I will be talking about Concept 8.1 in this recorded lecture. I'll be rearranging things a little bit from the book, since the order I'm going to be presenting is more of a logical progression than the one in the book. We will be discussing the laws of energy transformation as it applies to living organisms, the energy of life, and metabolic pathways. Before we go on to specific examples, let's talk about the laws of thermodynamics and how it relates to the energy of life. We will be discussing forms of energy and the laws of energy transformation. This picture shows different types of energy. First, let's define what we mean by energy. Energy is the capacity to cause change, usually to perform work. The diver on the top of the platform is waiting for his turn to jump off the platform into the water. He has a lot of potential energy, or the potential to change his position from the platform to the water, but he hasn't used it yet. The guy in the air is an example of kinetic energy, or the energy of the relative motion of objects. He is falling toward the water, so he is in motion, using kinetic energy to change his position from the platform to the water. Once he hits the water, he has less potential energy than he had on top of the platform. He has to use kinetic energy or motion energy of muscular movement to get himself up the stairs and back onto the platform. We will be using this example again when we talk about chemicals moving from higher potential energy states to lower potential energy states while releasing kinetic energy on the way down. For now, make sure you understand the difference between potential and kinetic energy. Now, let's talk about the laws of energy transformation. Energy can be transferred and transformed, but it cannot be created or destroyed. The cheetah in this picture is transferring the energy stored in the gazelle it brought down from the gazelle to its own body. The gazelle gained or transferred energy from the plants it had eaten. The plants gained their energy from the sun. The primary source of energy on the earth comes from the sun. On to the second law of thermodynamics. In any transfer of energy from one form to another, some of the energy is converted to heat, like in this example of the sprinting cheetah. Heat is non-usable by organisms to perform work, so it is lost to the organism. Remember, energy can be neither created nor destroyed, but it can be in a form of such low potential energy that it is no longer useful. To use the diver example, once you hit the water, you can't fall any further toward the water. You have to climb back up the stairs to the platform. The cheetah can't use the heat generated by its muscles to generate more muscular energy. It has to eat another gazelle, which is full of chemicals with high levels of potential energy, to generate more energy for its muscles. The second law of thermodynamics is why animals have to eat all the time. It's why plants have to have daily exposure to sunlight. To use another example, the second law of thermodynamics is why we can't take the exhaust from our cars and pump it back into the gas tank to make it go, although that would be wonderful. Let's go into more depth about the energy of life. One of the characteristics of life is the ability to maintain order over time. To do this, living organisms use chains of reactions or metabolic pathways. A metabolic pathway begins with a specific molecule, which is modified in a series of defined steps, resulting in a certain product. This is a generalized example, where we start at molecule A, which is converted into product D through a series of 3 reactions mediated by 3 different enzymes. Don't worry if this generalized example doesn't make sense yet. We will be talking about it in more detail as we go along. Metabolic pathways can be broken down into 2 different kinds of pathways or reactions within the pathway: anabolic reactions and catabolic reactions. In metabolism, anabolic reactions are connected to catabolic reactions and vice versa. Anabolic reactions are like climbing the stairs to the top of the platform. Anabolic reactions require energy to make larger molecules from smaller molecules. The larger molecules are higher up the potential energy platform than the smaller molecules are. Catabolic reactions are like the guy falling from the platform into the water. Catabolic reactions release energy in the process of making smaller molecules from larger molecules. The smaller molecules have less energy than the larger starting molecules. The energy released by the catabolic pathways fuel the energy needs of the anabolic pathways. Once again, don't worry if this makes no sense now. We will have specific examples later. At this point, I wanted to set the foundation for what we will be talking about later.